Thank you very much for your kind introduction. Also from my side, I would like to welcome you to the final presentation of my PhD thesis entitled Investigation of Active Materials and Polymeric Binders in Negative Electrodes of Lithium-ion Batteries. So nowadays, lithium-ion batteries are being used in many applications around us, from powering up our electronic devices, such as our phones, our laptop, tablets, to enabling renewable energy storage and electrical vehicles, as well as some critical applications such as medical or aerospace industry. With the energy transition demands and the shift towards sustainability, results in a global push towards renewable energy and electrical vehicles, and this increases the demand for lithium-ion batteries. So here in these graphs, we can see a global lithium-ion battery cell demand up to the year 2030, and it can be observed that 27% annual growth is expected until the year 2030, and most of these applications of the batteries is in the mobility sector. Therefore, there is a demand for advanced energy storage solutions with higher energy density, longer cycle life, safety, and sustainability. So no matter in which applications these batteries are being used or in which size or shape they are coming in, one thing which is in common in all the batteries and can predict the performance of the batteries is the materials which are being used inside the batteries. So these materials can be the active materials which can store the energy. It can be the inactive materials, such as binders, conductive additives, or separator, but it's not enough to only have suitable active and inactive materials. We need to also have a good processing of the electrode, and of course, we need to have suitable electrolyte formulation depending on the application of the battery. So the materials which are being used inside the battery not only need to be high performing, but they also need to be sustainable and environmental friendly, so that we can move towards the production of more green battery chemistry cells. In my work, I have been investigating the materials in the battery, especially silicon-based active materials and natural biopolymeric binders, in order to move towards the production of more green battery cell chemistries. This presentation will be divided into 4 different chapters. I will first start with the introduction and theory, moving on to the result part, which is divided into 2 sections of silicon-based anodes and polymeric binders, and finally, I will finish with the conclusion and outlooks. So starting with the introduction part, I will first go through the basic principles of lithium-ion batteries, moving on to the electrode design and manufacturing process, and finally, the active materials and polymeric binders for the negative electrode. Here we can see a schematic view of a lithium-ion battery. On the right side here, we can see the negative electrode or the anode of the battery, which the active materials such as graphite and silicon are used in this electrode. On the right side, we have the cathode, where we have the positive electrode, which is active materials such as lithium cobalt oxide, nickel manganese cobalt oxide, and so on are used. On the anode side, the electrode is coated on top of a copper current collector, and on the cathode side, the electrode is coated on top of an aluminum current collector. We also have the electrolyte within the lithium-ion battery, so the electrolyte can come in different shapes like the liquid electrolyte, polymer electrolyte, or solid electrolyte. In this work, liquid electrolyte has been used, which usually consists of a lithium salt such as LiPF6 and dissolved in some organic solvents such as ethylene carbonate, ethyl methyl carbonate, and so on. And then in between the electrodes, we have the separator. The separator is electronically insulator and ionically conductive. In this work, the main focus will be on the negative electrode or the anode of the lithium-ion battery. For designing the negative electrode, we start with the electrode manufacturing. The first step is the slurry mixing. This is where we are mixing the binders, active materials, and conductive additives together. Here we can control the formulation of this slurry, the viscosity of the slurry, and the homogeneity and mixing methods, which can have an effect on the next step, which would be the coating of the electrode. So then after preparing the slurry will be coated on top of a copper current collector, And here different coating methods can be implemented, and the thickness of the electrode can be controlled, which can have an effect on the areal capacity of the electrode. The adhesion to the copper foil and the uniformity of the electrode is of high importance. The next step would be calendaring the electrode. Here we can control the thickness and porosity. And then finally, before using the electrodes in a battery, they need to be dried under vacuum to remove the traces of moisture. In addition to the manufacturing process, the electrode materials are also of high importance. What type of active materials we're using, the binder materials, conductive additives, as well as the current collector. So here is an image of the electrode coating process that I have been used in the lab. Here in this drawbar, this is where the slurry goes, and by moving of this plate with a constant speed, the electrode will be coated on top of the copper current collector. And different parameters such as the speed, temperature, or the thickness of the coating can be controlled in this step. And finally, we will see the final result, which is the anode, which is coated on top of the copper current collector. Then, so what kind of active materials are being used in the negative electrodes? The most commonly used active material is graphite, as it is schematically shown here. We are seeing the graphite layers, and during lithiation and dilithiation, the lithium ions can intercalate and deintercalate in between the layers. The benefits of graphite is that it has a low cost, it has a long cycle life, it shows a high coulombic efficiency, a stable solid electrolyte interface, and it has a low working potential. In addition to that, also graphite shows a low volume change upon lithiation and dilithiation of the battery. But the disadvantage of graphite is its limited theoretical capacity of 372 mAh per gram, and this limits the usage of graphite in high-energy battery applications. So other active materials have been investigated, and one of the promising active materials is silicon. In silicon, during lithiation and dilithiation, alloying and dealloying will happen. And the advantage of using silicon is that it is highly abundant, it has a low cost, and it's environmentally friendly. Also, it has a high theoretical capacity and a low working potential. But despite all these features, silicon goes through a large volume expansion upon charge and discharge. So when we lithiate a silicon electrode, the silicon particles expand, and this can result in cracking in the silicon particles and in the electrode. And then after cycling the electrode for many cycles, and due to this constant volume change of silicon, we will have pulverization, delamination of the particles, loss of contact from the copper current collector, unstable solid electrolyte interface, and also it shows a lower coulombic efficiency compared to the graphite electrodes. So what kind of strategies can be used to implement silicon into the anode of lithium-ion battery? One strategy is combine using graphite and silicon together in the anode. So this way we will have the benefits of both active materials, which would be the higher specific capacity compared to pure graphite electrodes, and it would be lower volume change and more electrical conductivity compared to pure silicon electrodes. Another strategy which can be used is using suitable polymeric binders. So binders in the electrodes are like a glue, which is holding on the active material and the conductive additive together, and is also adhering them to the copper current collector. So the binder not only needs to show a good adhesion between the active materials and the conductive additive, but it should also have a suitable adhesion towards the copper current collector. The binder should also have good mechanical properties, especially in case of silicon. This is of high importance because of the constant volume change of silicon. So the binder needs to be highly elastic and flexible so it can accommodate to the volume change of silicon particles. Also, the binder needs to be stable against the electrolyte, and it also needs to be thermally stable upon drying process of the electrode and the application temperature of the battery. The conductivity of the binder is also an advantage if the binder is electronically or ionically conductive. And also the binder can have an effect on the dispersion of the materials in the slurry and the slurry viscosity. And one important factor is that these binder materials need to be sustainable and environmental friendly and having a low cost. In general, binders can be divided into two groups of non-aqueous binders, such as PVDF, which is commonly used in the anode and cathodes of lithium-ion batteries. So PVDF can be dissolved in NMP solvent, which is a toxic solvent, and it requires a higher drying temperature for the electrode, and also it is more expensive. And suitable equipments are required for collecting these toxic vapors during the production of the battery and the drying process. On the other hand, we have the aqueous binders. Aqueous binders are more environmental friendly, and they are less expensive and require lower drying temperatures for the electrode. Some of these aqueous binders are coming from natural sources, such as carboxymethyl or chitosan, so this results in a more green synthesis approach of the binder, and also this would be an advantage later on during recycling of the battery. So as mentioned so far in this work, two different strategies have been used to use silicon in the negative electrode of lithium-ion battery. One is using a silicon graphite electrode, using graphite for stability and silicon for high capacity. And the other is using polymeric binders for a better mechanical property of the cell and also sustainability of the electrodes. So in the next section, I will go through my results on the silicon graphite electrodes. So first of all, the formulation of the silicon graphite electrode was optimized. As it can be seen here, different ratios of silicon to graphite was used, from pure graphite to pure silicon. And it should be noted that the silicon which was used in this work is a silicon alloy, but for simplicity during this presentation, it will be referred to as silicon. A dual binder system was used with this electrode using lithium polyacrylic acid and carboxymethyl. And finally, the different ratios of binders were also investigated to further optimize the electrode formulation. After the anodes were prepared, they were assembled in the coin cell against lithium metal, and the electrochemical performance of the cells were investigated. So in this graph here, we can see the capacity versus cycle number for different electrodes with 10, 20, 40, 60, and 70 weight% silicon. And as it can be observed, by increasing the amount of silicon, we are showing less stable cycling performance and a more rapid capacity loss. If we compare the capacity retention of these electrodes after 500 cycles, this value is 98% for the electrode with 10 weight% silicon, and it reduces to 4% for the electrode with 70% silicon. And among these electrodes, the electrode with 20 weight% silicon showed a more stable performance, and after almost 900 cycles, it shows a capacity retention above 80%. The irreversible capacity of the electrodes were also investigated. So the irreversible capacity is the difference of lithiation and dilithiation capacity. And then the accumulated irreversible capacity was calculated, which is the sum of these irreversible capacities up to a certain number of cycles. So this can indicate us the active lithium loss, SEI layer formation, lithium metal plating, loss of active materials, and the parasitic reactions which are happening in the battery. The lower accumulated irreversible capacity shows a better performance of the cell and a higher Coulombic efficiency. Here we can see the accumulated irreversible capacity versus cycle number for different silicon graphite electrodes with different silicon to graphite ratio. As it can be observed, in a lower silicon content, we are having a more linear behavior and a lower initial slope, which indicates the more stability of the cells upon cycling. By increasing the silicon content, we are having a higher initial slope, which indicates a more rapid degradation, and the shape of the curve is changing from linear to a sigmoidal shape. And this faster rate of accumulation can result in accelerating the degradation process. Also, if we have a look at the initial accumulated irreversible capacity, this is also increasing with the increasing the amount of silicon content, which shows that we are having a higher capacity loss in the first cycle for the electrodes with the higher amount of silicon. Based on this graph, we can understand that there should be a trade-off between the capacity of the electrode and the stability of the electrode. Then the differential capacity analyses were performed on the electrodes with different silicon content, as well as pure graphite and pure silicon. Here we can see the normalized dQ/dV, and as it can be observed for the graphite curve, the black curve, we can see the lithiation and dilithiation peak, which is marked with the blue triangles. And we can see that by increasing the amount of silicon, the intensity of these peaks, the graphite peaks, are decreasing as it is expected. And then on the other hand, with increasing the amount of silicon content, the specific peaks for the intensity of the specific peak for silicon is increasing. Then the electrode with 20 weight% silicon was also measured after 900 cycles. And here we can clearly see the peaks which are related to silicon and graphite. And this indicates that after 900 cycles, we are seeing the capacity in this electrode because of the participation of the graphite and silicon active material. And it is not due to lithium plating or stripping. Here we can see the electrochemical performance of the silicon graphite composite with 20 weight% silicon, as well as pure silicon and graphite electrode. And here we can see the synergistic beneficial effect of using a silicon graphite composite, which is increase in the capacity compared to the silicon electrode, and a better cycling performance compared to the silicon electrode. The rate capability of these cells were also investigated at different C rates, and afterwards the cells were measured again at C/10 to measure the capacity recovery. It can be observed that for the pure silicon electrode, we are having a more rapid capacity loss and an unstable performance, and also lower capacities at high C rate. After measuring the capacity recovery at C/10, it can be observed that for the composite electrode and for the pure graphite electrode, we are having 99% capacity recovery, while this value is 88% for the pure silicon electrode. And based on the electrochemical measurements which have been shown so far, the silicon graphite electrode with 20 weight% silicon was chosen as the optimized silicon content in this work. The morphology and structure of the silicon particles of the silicon electrode was also investigated using SEM-EDX analysis. So firstly, the pristine electrode was investigated to see the structure and the morphology of the electrode before cycling. And after cycling, the cells were disassembled, and the anode was investigated using SEM and EDX to see the structural changes which happen after electrochemical cycling. Here we can see a cross-section SEM image of pristine silicon graphite electrode with 20 weight% silicon. In the top image, we have a panoramic view of the electrode, and we can see that this film is homogeneously distributed on top of the copper current collector. If we further zoom in, we can better see the structure of the cell, and based on the EDX mapping, here we can see the distribution of graphite particles shown in purple and the silicon particles in blue. If we further zoom in into the structure of the electrode, based on the EDX results, here is how a silicon particle structure looks like before electrochemical cycling. After almost 1,200 cycles, the cells were disassembled, and again, the morphology of the electrodes were investigated using SEM and EDX. Here we can see a cross-section SEM image of the electrode after electrochemical cycling. And if we further zoom in, we can better see the structural changes that happens in the electrode. And mostly we can see a gradual loss of silicon volume fraction, and this can be due to the volume change of silicon upon charge and discharge, which can result in more degradation, delamination of silicon particles, and formation of crack and pores. In this image, we can also see different stages of silicon degradation. So by looking at this particle, which is marked with a green circle, we can clearly see some signs of cracks on the particle, but the morphology is more or less similar to the pristine electrode. Then we have this particle here, which is marked with orange, and here we are seeing more degradation of the silicon particles and the change in the morphology. And then there are some areas which are marked with red. We can see complete degradation of the silicon particles. So based on this SEM image here, we can say that one reason that we are not reaching the theoretical capacity of our electrode could be that some of the particles, for example, like this green particle, is not contributing to the lithiation and delithiation as much as the other particles which are marked in orange and in red. Here is a closer view of how the particle looks after electrochemical cycling. We can see a clear visible crack here and also the degradation and the loss of volume fraction of silicon particles. Then the electrochemical performance of the anodes were measured at high temperatures. For this measurement, an electrolyte with a high temperature enabler additive of TeOSCN was used, which was previously investigated in our group by Felix Auperle. And here we can see the rate capability of the cells at room temperature, 45 and 60 degrees. If we look at the capacity recovery of the cells, we can see that for room temperature, we are having a highest capacity recovery and a lowest capacity recovery for 60 degrees. At low C rates, we can see that there is less difference between the capacity at different temperatures, but by increasing the C rate, high temperature plays more roles in the transport kinetics, and we are seeing more capacity at higher temperatures in case of the half cells versus lithium metal. Then the electrodes were assembled against NMC622 cathode in the full cell, and the same measurements were done in the full cell. And we can see that the capacity recovery of the electrodes is lower compared to the capacity recovery that we observed in the half cells. And here we can see that the electrodes, that the cells at higher temperatures show a lower capacity compared to room temperature. And we can say that with increasing the temperature, there is a benefit of lithium-ion diffusion and increasing the reaction kinetics. But also on the side, this will increase the degradation mechanism, especially in the full cell and in the cathode electrolyte interface, and resulting to less capacity compared to room temperature. With that, I would like to give a short summary of this section. So the optimization was done on the anode formulation using silicon and graphite as active material. Different ratios of silicon to graphite was investigated using a dual binder system, and the electrode with 28% silicon was chosen as the optimum content. The postmortem analysis was done on the electrodes before and after electrochemical cycling using SEM EDX investigations. And the electrodes were also investigated in a full cell against NMC622 cathode. In the next section, I will go through my results on the polymeric binders in silicon graphite electrodes. So one of the binders that I have already mentioned, which is commonly used in silicon-based electrodes, is lithium polyacrylic acid. And in many publications, it has been referred that the low pH of LiPaA has a beneficial effect on the mechanical and electrochemical performance of the electrodes. So during my work, I had the question if the pH of the binder plays a role in the performance of the silicon-based electrodes. And therefore, I have investigated the neutralization degree of the LiPaA binder, which is directly related to the pH of the binder. And this pH can have an effect on the electrode performance during production and electrochemical cycling. So different ratios of lithium hydroxide to PAA was investigated, which is directly related to the pH of the binder. The binders were initially directly coated on top of the copper current collector, and after drying at room temperature, it was observed that the binder with a lower pH was delaminating from the copper current collector, and also we can see a change in the color to a blue-green color. This effect is less pronounced in the pH 6, and for pHs 7, 8, and 9, we can see a transparent color of the binder and a good adhesion to the copper foil. The binders were detached from the copper current collector, and ICP measurements were performed on the binders, and it was observed that at lower pH, we are seeing a higher copper content in the binder, which is the reason why the color of the binder is changed to a blue-green color, and this effect is less for the higher pHs of the binder. And this can be due to the atmospheric corrosion of the copper current collector in connection to the acids within the binders, which are having a lower pH. The thermal properties of the binders were investigated using thermogravimetric analysis, or TGA. So here, the weight of the sample were measured depending on the temperature, and it is observed, and then afterwards, the first derivative of the thermogravimetric analysis was measured, the DTG curve, for the PAA powder and LiPAA with different pH of 4, 6, 7, 8, and 9. Based on this graph, in the first region, we are seeing a peak at 40 degrees due to the free water, and the peak due to the absorbed water is seen at 80 degrees for PAA, and this value increases to 115 degrees for the LiPAA with a more basic pH. So this is an important thing to think about when drying the electrodes, which are using the binders with a more basic LiPAA. In the next section, we can see the dehydration of carboxylic acid groups, which happens around 150, and this is less pronounced for the higher pH of the binder. Then in the next section, we can see the decomposition of PAA and LiPAA with pH 4, and in the final stage, we can see the main chain and side group breaking above 400 degrees. These LiPAA binders were used in the electrode, and the mechanical property of the electrode was investigated using a 90-degree adhesion peel test. Here we can see the electrodes after the adhesion test, and here we can see the average peel strength at different pH. It can be observed that for pH 6, we are having a lower peel strength, and as it can also be observed here, we can see that the whole electrode is stick to the tape after the measurement. So this can indicate that the failure here is due to the film current collector interface. At higher pHs, we have a higher average peel strength, which is again decreasing by increasing the pH to 9. And in the basic pH, we see that the electrode is still sticking to the copper foil, but some parts of the electrode is sticking to the tape after the measurement. And this indicates that there is a failure within the bulk of the electrode. Also, it should be noted that the pH of the binder has an effect on the viscosity of the slurry. So for lower pH binders, we are seeing a lower viscosity and therefore more difficulty in coating the electrodes. And at higher pHs, we also see a more viscous slurry, and this also brings a difficulty in terms of coating. So therefore, there should be a balance between the peel strength and also the viscosity of the binders, which in this work, a neutral binder between 7 and 8 was chosen as the optimized pH of LiPAA. Also, if we have a look at different pHs, it can be seen that at lower pH, we can have more the formation of more stronger and covalent bonds, which is more irreversible, and it can result into the plastic rupture upon charge and discharge. And then with the increasing the pH of the binder to more neutral pHs, we are having more strong supramolecular interactions like hydrogen bonding and ionic bonding, which will also have recovery after a huge volume expansion of silica. Then the cross-linking of a lithium polyacrylic acid binder was investigated with carboxymethyl cellulose. So here in this image, we can see the rate capability of cells with the cross-linked and uncross-linked binders using LiPAA and CMC. And in terms of cross-linking the binder, we can form a 3D network, which can better accommodate to the volume change of the silicon. And it can also bring a balance between the strength and reversibility. At a lower C rates, we can see more similar performance of these electrodes, but at higher C rates, we can see up to 60% capacity enhancement in case of cross-linking the LiPAA binder with CMC. Also, another binder that I have investigated during my work was a chitosan binder. Chitosan is produced from chitin, which is a highly abundant biopolymer on Earth. And due to its good mechanical properties, it can be found in the shell of shrimps, crabs, some insects, and fungi. By partially deacetylation of chitin, we can produce chitosan, And chitosan is widely used in medical and pharmaceutical application, in food industry, and it can also be implemented into the energy storage applications. If we have a look at the structure of the chitosan, we can see acetylated and deacetylated units, and one of the factors which can have an effect on the properties of the chitosan is the degree of acetylation, which is the number of acetylated units divided by the total number of acetylated and deacetylated units. Another factor would be the degree of polymerization, which is the number of monomers which we have in our chitosan biopolymer. So in the next slides, the term dA will be used for degree of acetylation and dP for degree of polymerization. This work was done in collaboration with the Biology Institute in Münster, and we have received 5 different samples with 3 different degrees of acetylation of 50, 30, and 0. And for the degree of acetylation 0, we had 3 different degrees of polymerization. First, the chitosan biopolymers were investigated using FDIR measurements. And here we can see at 3,400 the OH stretching and the NH extension vibrations. Also for all the samples, we can see the CH stretching. And in the region between 1,500 and 1,800, this is where we can estimate the dA of the chitosan binder due to the amide and amine bands. So for the chitosan binders with higher degree of acetylation, we can see amide 1 and amide 2 bands, and also the CH binding and symmetrical CH3 deformation in this region, which we are not seeing this for the chitosan with DA0 as it is expected. And for the DA0 samples at 1,600, we are seeing the primary amine groups. Then the binders were implemented into the silicon graphite electrode using the benchmark electrode, which was discussed in the previous chapter. And in that electrode, a 10-weight% binder of lithium polyacrylic acid and CMC was used. So the same formulation was done by using 10-weight% chitosan binder in the slurry. And these electrodes showed a good cohesion of the film, but there was not sufficient adhesion to the copper current collector, and after drawings, the films were delaminated from the copper current collector. Therefore, here we can see that by only changing one factor like the binder in the electrode, we need to further optimize the electrolyte formulation for this specific binder. And the optimization was done on the silicon graphite electrodes using chitosan binders, and a different amount of binders were investigated, and 4-weight% binders showed a balance between the cohesion of the electrode and adhesion to the copper foil, and the ratio between the silicon graphite active materials were maintained the same. So here we can see the slurry formulation using the chitosan binder with 4-weight% binder, and here we can see the benchmark lithium polyacrylic acid CMC binder. After preparing the anodes, they were assembled against lithium metal, and the electrochemical performance of the half cells were investigated. Also, one reference cell with lithium polyacrylic acid and CMC binder using 4-weight% binder was prepared in order to compare it with the chitosan binders. As we can see here in the half cell performance, we can see a stable electrochemical performance for the chitosan binders, especially for the chitosan binders with DA50 and DA01, which are showing a very similar performance to the reference LiPAA CMC binder. And they are having a high capacity retention of 80% after 300 cycles. Then the rate capability measurements were performed on the electrodes, and here we can see that except one of the chitosan binders, the others, they all show a capacity recovery in the range of 96 to 97%. The electrodes were assembled in a full cell against NMC622 cathode, and again, the electrochemical performance of the electrodes were investigated. And here we can see that the cell having chitosan with DA50 shows a higher capacity compared to all the other electrodes, also compared to the reference electrode with lithium polyacrylic acid and CMC binder. In case of DA0 binders, again, we can see that DA01 has the highest capacity and a higher Coulombic efficiency, and this is the binder which had the highest degree of polymerization, similar to the degree of polymerization of DA50. Again, the rate capability of the cells were investigated in the full cell. And here we can also see that in all C rays, we are having a higher capacity using chitosan with DA50. And we are also seeing a stable performance in these cells and a capacity recovery higher than 80% after deep lithiation and delithiation at 5C. So based on the electrochemical measurement, a chitosan with degree of acetylation 50 was chosen as the optimized binder to be used in our silicon graphite electrodes. And this can be due to the high number of acetyl functional groups, which is present in this binder, which can form a hydrogen bond with the surface of the silicon and improve the mechanical performance of the electrodes. Then the cross-linking of these binders were investigated using citric acid to form a 3D binder network and also improve the performance of the electrodes upon cycling. The different ratios of DA50 binder to citric acid was investigated, as well as DA50 binder and pure citric acid. The measurements were, the FTIR spectroscopy was done. And we can see that at 1721, we have the carboxylic groups in citric acid. And then in this region, we can see that in cross-link binders, we can see the formation of amide bonds and the secondary amide groups. And as we can see here, this peak becomes sharper with increasing the amount of cross-linker. Also at 1650, we can see that the peaks move towards the lower wave numbers. And based on these FTIR measurements, we can observe that we had a successful cross-linking of the binder. Also, the thermal properties of the binders were investigated before and after cross-linking with differential scanning calorimetry. And it was observed that the decomposition temperature of the chitosan was also increased after cross-linking with citric acid. As I mentioned before, the chitosan binder showed a good cohesion of the film. So this brings the idea of producing the so-called freestanding electrodes to eliminate the use of a copper current collector to reduce the weight and increase the flexibility of the electrodes. Therefore, the anodes were directly coated on top of a separator. And here we can see the electrochemical performance of the electrodes against NMC 622 cathode using freestanding electrodes and the electrode coated on top of a current collector. And in case of the freestanding electrodes, I have also used the pure DA50 chitosan and the cross-link binder. It can be observed that for both of the freestanding electrodes showed higher capacity and better performance compared to the electrode which is coated on copper foil. And this can be due to the reason that by eliminating the copper foil, we will reduce the corrosion and the degradation products that can happen on the current collector, which can result in adhesion loss and a loss of electrical contact, which can result into the capacity loss of the cell. And comparing the freestanding electrodes with and without cross-linking, we can see that initially they are showing a similar performance, but at long-term cross-linking is improving the performance of the cells. With that, I would like to give a summary of this section. So polymeric binders were investigated. Firstly, the lithium polyacrylic acid was investigated and the effect of pH, and cross-linking was investigated on LiPAA. And then the chitosan natural biopolymeric binder was investigated with different degrees of acetylation and degrees of polymerization. The electrode was optimized, and cross-linking and freestanding electrodes were performed. With that, I will move into the conclusion and outlooks. So as it was mentioned in the motivation slides, in this work, I have investigated the materials on the anode of the battery to have high performance and environmental friendliness so that we can move towards green battery cells. In the first section, active materials were investigated. Silicon graphite electrodes were optimized, and it was seen that the 28% silicon shows the optimum performance. A dual binder system of lithium polyacrylic acid and carboxymethyl cellulose was here, and postmortem SEM-EDX analysis was performed on the electrode to observe the degradation of the electrodes after electrochemical cycling, as well as the full cell investigations. In the second part, polymeric binders were investigated, such as LiPAA, or natural polymeric binders such as chitosan, which chitosan results in a more aqueous processing of the electrode, and we could reduce the binder content in this electrode and produce the freestanding and sustainable chemistries on the anode side. So by combining using these binders and the optimized silicon to graphite ratio, we can produce more green and environmental friendly negative electrodes on the batteries. But in order to move towards a complete green battery cell, more steps can be done in the future. So one thing that can be studied in the future is that in this work, I investigated one type of silicon and one type of graphite materials. This work can be expanded to investigating different type of silicon and graphite materials and to see how the binders interact with different type of silicon and graphite. Also, it should be noted that the lithium in the lithium-ion batteries is coming from the cathode side. So the cathode also needs to be further investigated to use more sustainable chemistry, which is adaptable to be used with the silicon graphite electrode. The electrolyte is also of high importance, especially in case of increasing the amount of silicon. And the impact of electrolytes, such as the electrolyte additive or the electrolyte salts, can also be investigated on the electrodes and the binders. Also, the potential for alternative coating approach, such as dry coating, can be investigated. And one important factor which can be investigated in the future is how these binders can have an effect on the recycling of the battery later on. Thank you very much for your attention.